Hello and welcome to this third part of lesson two. In the first two lessons, we'll learn about stress-strain relationship and how to understand the look of it and derive some attributes, an understanding of the material itself represented by this relationship in terms of its ductility, resilience, and toughness. So now we'll switch gears a little and start trying to think about generally how a point feels stresses. And generally here I mean by a point in a material in 3D with 3D forces all over the place, how we can represent the stresses acting on this point, which will use stress blocks, 3D and 2D, and show on that stress block the different components of stresses of different type of stresses that we have learned so far, which are mainly two types, normal stresses and shear stresses. So if we look at this nice potato here, so kind of a general representation of a shape, like a potato shape here, there are different forces acting on that shape. If I do a cut somewhere in this potato, take out the right half of it, throw it away, but still I need to represent the action of the forces P3 and P4, it's their representation or their influence or impact on every point of that cut. So when I start analyzing or kind of design this potato, I know this point will feel that type of stress, this magnitude, this direction. So let's look at this point Q in this cut that I made, and I want to represent the internal forces acting on that point represented by delta A, small area delta A. And we learned before that we have only two types of stresses, right? The normal stress delta F and shear stress delta V. Now I don't know where's the direction of delta V. It depends on the equilibrium of P3, P4 with P2 and P1 on the other side. So I know there is a shear at any point. This shear can be this way, it can be this way, it can be this way. So let's assume that from equilibrium, I know there is a shear and acting in one direction, right? Like I know there is a normal force acting on this little area, delta F, and it's from its definition, normal force is always perpendicular to the cut face. So knowing that this point I represented, it's what it feels from equilibrium of P3 and P4, it feels delta F, normal force, little one acting on this little area, and delta V, little shear force acting on this area. So knowing that now, I can actually, now this V in this direction here, and by the way, the cut here, I didn't mention that, but the cut is perpendicular to the YZ plane, meaning that it's perpendicular to the x-axis. So it's parallel to the YZ plane. So this means it's perpendicular to the x-axis. Now if I try to get the components of this delta V in this YZ plane kind of cut, I will end up with two components, delta V xy and delta V xz. So we have to be a little careful about the notations here. You see delta Fx, delta Vx, delta Vx. X here refers to the idea that these stresses are acting in the plane of a cut. This cut is perpendicular to the x-axis. All right, so delta Fx is in the plane perpendicular to the x-axis, and because it's normal force here, this normal force is actually in the x direction, so that matches pretty well. But delta Vx and the other one, delta Vx, they are in the plane that's perpendicular to the x-axis. So the plane perpendicular to the x-axis. Now to differentiate between these two components, I add another subscript here, y and z. So now this one is acting in this plane perpendicular to the x-axis in the y direction, and we can do the same reasoning for this one, delta V x z. So I got these little forces. I started with the two main one, the normal and shear, and then broke down the shear in somewhere in that plane into the direction I know, which is the y and z directions. Now considering that this little area, if I want to calculate the stress is the force over the area. If this delta A gets smaller and smaller and smaller to almost to zero, then I will calculate the limit here, which will give me now the stresses. So this is my goal here, to end up with stress sigma x at this point that it feels. So now the point is really point, not a block or a square. And tau xy and tau xz. Sigma x came from delta f over delta A. Tau xy came from delta Vxy divided by delta A, and tau xz is following the same thing. So this is what point Q feels when I do this cut, which is perpendicular to the x-axis, and deal with the left side of this cut. Now I can do all kind of kung fu or karate cuts, so I can do a cut perpendicular to the y and deal with the top part of it or lower part of it. I can do cut perpendicular to the z, still at the point Q, either deal with the left part of it or the right part of it. I can stick to the x, cut perpendicular to the x like here, but deal with the left part, not the right part we have here. So the idea is now every point within a material, I can represent it with a block of stresses. And this block is referring to the different cuts I can make in orientation, with orientation to my XYZ axes. So all of what you did so far is only getting a stresses on only one face of it. So let's see here how we can use what we learned so far to kind of come up with the way of calling and labeling stresses on this block representing a point in a material. So if I open here, 1 minute. Now I see here it's exactly the same thing, but let's work out now the how we're going to label the stresses. So every block face will have or a cut face will have three types of stresses. Actually, there are two types, but one type can be broken down into two components. So normal stress and two shear stresses. And the shear stresses from definition parallel to this face, but they are in the direction of the axes of the plane of this face. So if I think about first the normal stresses, I will see that I have for every face visible to me, and I'm here, visible means I only see three, but there are three left in the back I can see. So just to stress here, I can draw on what I see, but there are stresses that I didn't draw yet because I can draw them, I can see them. But we'll see other ways to show them actually. But how to show stresses that are not are hidden kind of, I can draw side view of this block and draw a 2D block of stresses. So when I draw this, I can see here sigma x and sigma y that I drawn on the faces from the 3D block. And now I have a version of the 3D as a 2D stress block. Now if I think about shear stresses, how I can call shear stresses and label them on these many faces of this block. So like we said in the previous slide, every face will have two tau or shear stresses. So for this one I just draw here, it's tau xy, it's tau in the face of the block that's perpendicular to the x-axis, and it is in the y direction. I can draw tau xz. It's in the tau in the face perpendicular to the x, that is in the z direction, and you can see all of these now different taus acting on the three faces that are visible to me now. Now, if I project these shear stresses from the 3D on the 2D block I have, I will see only two of them acting within this plane of projection, because my side view here is only showing the X and Y plane of stresses. So I can only see sigma X and sigma Y. I can see tau XY and tau YX. But I cannot see tau YZ because it's not acting in the plane that I'm trying to view, which is XY. Tau YZ is kind of going into my eye. Tau ZY and tau ZX are not in the plane. They're not in the plane I'm viewing. So kind of I'm trying to see what stresses are acting on the faces that I see, kind of their frame. So anything other than that, I will ignore. So because the point here, I'm trying to analyze the equilibrium of that 2D block. Now, considering now equilibrium, so I'm not analyzing equilibrium here. If I do the sum of forces in X and Y, so in 2D equilibrium I have three equations, and I'm applying two of them now. So sum of forces in X and Y are equal to 0. This means that when you do equilibrium, you will have similar stresses to what we have in two faces so far. The other two faces will have similar stresses but reversed. So I have sigma X and sigma Y, but now on the opposite side, and tau XY and tau YX opposite to the ones I have drawn before. Now I didn't use yet the third equilibrium equation, which is sum of the moment around a point. I'll pick the point here in the middle of the block, which I kind of can move the z-axis to be in the middle of the block here, and trying to see what's the equilibrium here. So can I relate here? I know sigma X and sigma X on both sides are equal. What about tau XY and tau YX? So when I try to put some dimensions to this little space, if let's say every side of this block is A, lowercase, and the area of every side of the block is delta A, because I need to calculate the forces that come out of these stresses, because a stress is not a force. So multiply, trying to take the moment around Z now, sigma X and sigma Y go through this Z point, or the Z axis here, so they don't cause a moment around it, so there's no moment from sigma X and sigma Y. But tau XY, there are two of them, two tau XY. One is going up, one is going down. If you remember from statics, remember couple moment. So I can represent the moment from these two forces that are equal and opposite by multiplying one of them with the distance between these two forces equal and opposite. So that's a couple moment. So a couple moment from the two tau XY forces times the delta A, the couple moment is just multiplying that by delta, by A lowercase. Similarly, I can do the same for tau YX. So tau YX going to the right, going to the left, just focus on one times the distance between both tau YX forces here. So if you do the equilibrium, you'll find actually that tau XY is equal to tau YX. So that shear force on that right face is equal to the shear force acting on the top face of that block. So if I have a point, the longitudinal stress would be equal to the transverse stress, shear stress. We'll see more of that when we cover the design of beams and shear and beams. So this tau XY is equal to tau YX. I got it from the equilibrium of this specific 2D block of the XY plane. I can do similar equilibrium when I analyze the 2D view, when I look to the YZ frame or plane of this block, and to the XZ plane when I look from the top. And you will find similar conclusion that tau XZ is equal to tau ZX, tau YZ is equal to tau ZY. So this is kind of how we represent, label the stresses acting on the 3D block of any point in space. And we can also relate between the shear stresses acting on these faces of the block. Normal stresses are easy. If you have sigma x acting on one point, remember it's a point. So if there is a stress in this direction, then it feels a stress in the other direction, equal and opposite. So going back to here to the slides, and the idea of representing stresses of point in a general form, which is the 3D block, will be useful later and analyzing transformation of stresses and very interesting stuff in the future. So this is kind of the summary of what we have done just a moment ago. So let's see how we can use that in representing stresses in maybe a simpler form or a simpler case, but still following kind of a similar process. So let me open this exercise here. So now the question here is asking what will draw the generalized stress block and the stresses on this block for point Q for this specific loading case of the bolt. So what happens is do a cut at Q. So I'll do a cut, take out the lower part of the bolt with the forces acting on this part, and this is the free body diagram, but it's not complete yet because I need to draw the internal forces. I can only have here focus on the shear, so I can have a moment, but it's very minimal in this case, and there are no normal forces. So the shear from equilibrium would equal to P. And I can now calculate tau, the average shear stress on that section here, which will be felt in every point of that section. It's an average shear stress. It's V over A, or in this case, P over A, because P is the shear. Now, if I imagine I represent this dot, if I represent it with a little block, and I take this block, zoom too much into it, and this tau I calculated is just acting on that face. Now, remember the potato example, when we did the cut, this cut was only one face of a 3D block. Similarly here, that face, that square shape here, is a face of a 3D block representing the point, and the stress is acting on this point from all different sides. Now from equilibrium, I know I have only shear stress on that face of that block, the top one. Knowing what we learned from before, shear stresses cannot exist by itself on one face. It's not in equilibrium, so I need to complete the block knowing only one face, which is kind of magical here. So using what we learned before, I know that from the sum of forces in X and Y, there should be a shear force developing opposite to tau that I have on the top, developing in the lower face, right? So that's the sum of forces in X. I can figure this out. From also the equilibrium sum of the moments, I have to develop also an opposite couple to these two tau, the horizontal ones. So opposite couple, and I want to have it couple because the forces will cancel each other, but the couple will resist the couple I have from the horizontal tau that I had before. So that's basically here the block, the stress block that's representing the stresses acting in Q. So even if like I have horizontal shear forces in the bolt, so clearly resulting in the shear stresses going horizontally, but the point also feels vertical shear stress happening, which is interesting. So that's the end of this part here. We'll learn about 3D stress blocks. Very important topic here. We will build on it more when we deal with transformation of stresses and more circle. But it's important to introduce it early like this in the class, so you will understand that a point will have normal and shear stress can be having components in X and Y. And that's only one face, one cut through this point. I can do many cuts, many orientations, but I can represent it in a standard way using the 3D stress block. Thank you for watching, and I will see you in future videos.